Welcome. We were discussing on link power budget, and on that we have discussed the power part of it, that is signal power, how it is transmitted, how much it is received, what are the losses, and then we have also briefly discussed about the noise, how it is generated and in the components, and that how that noise figure and noise temperature is defined, and in a cascaded system how it can calculate it, and the receiver noise temperature and noise figure, how it can calculate it. Now, in addition to the receiver, in front of the receiver, in fact, we have an antenna that is there in the satellite receiver as well as in the ground receiver. So, let us see whether antenna receives a noise in addition to the signal and what is its characteristics. So, today we will discuss about the antenna noise first. So, we will call it antenna noise, and since we are talking about the converting the noise into a temperature form, so we will call antenna noise temperature. Now, antenna is let us draw it from the ground. So, this is an antenna which is on the ground, and it has a beam which is like this, and we have seen that at the center of the beam, which is bore side, the gain is maximum, and as it deviates from the axis of the maximum gain, the gain slowly falls depending on how the antenna is designed. In this case, I have shown a parabolic reflector antenna. Now, gain is reduced means whatever signal or power it is coming in this direction, antenna output will receive less compared to if it is received at the on axis maximum gain. So, the noise when it is looking towards the, let us say ground antenna is looking towards the sky, the other objects are radiating from the sky, noise is coming like this, noise is coming from here, noise is coming from, there are small lobes through which also it receives, and there are nulls in between, that is the antenna characteristics. So, some power is received here, and whichever noise is coming in this direction, it goes into null. So, like that from various angle noise is coming. So, therefore, the antenna noise output, that is antenna noise output, it depends on the radiation pattern, which is depends on in r theta phi coordinate system, which is depends on azimuth elevation or the phi and theta. So, it output depends on the radiation pattern, and in this radiation pattern, in all direction the surrounding radiations are not coming, surrounding emissions are not coming uniformly, noise is coming from one direction more, some direction it will may be less. So, it depends on surrounding emission. So, the whole thing of this, how much noise is received at this point, can be called as if a resistive noise is appearing. We can call it a effective noise temperature, as we have seen in the other part of the receiver. And since it is on the antenna, so antenna effective noise temperature, let us term it as T of antenna. It is as if equivalent noise resistance or noise source is there, which has a effective noise temperature which is appearing at this point. So, whole thing is modeled now. Now, let us see there are scenarios which is in two direction. One is the satellite antenna, now satellite antenna is let us say this is the satellite solar panels, and here is the ground. Let us say this is the north part, and satellite antenna is looking towards the ground, and we have calculated that for geostationary satellite, for a global beam we have beam of 17.4 degree, which is a 3 dB beam width and all these things. So, for our purpose, if there are smaller than global beam, then also the purpose is communication with earth. So, the satellite antenna is looking at the earth. So, all in addition to the signal power, the noise power which is coming from earth will be seen by this satellite receive antenna. And what really that noise power sees in this, there are land part, there are ocean part, there is a pole which is the ice are there. So, therefore, it sees a land which has a higher temperature, obviously it is radiating more temperature. Then it sees ocean, comparatively less temperature, and then it may see the polar region which is almost ice, that is much lower temperature. So, different part of the earth will have different temperature, and the satellite is moving around the earth depending on which location it is located. So, therefore, different antennas from satellite will see, depending on the antenna beam, whether it is a global beam or spot beam, it will see some different type of temperature. On the average, people say let us take 290 degree Kelvin, just a thumb rule number, 290 degree Kelvin is getting from the earth side. Okay. That is, now satellite antenna, you can see that it is towards the satellite, the communication is towards the satellite. So, in other way we can say the satellite antenna seeing this noise in its uplink, that is from earth to space, that is what we call upward, though here it is drawn like this, it is upward to the satellite. So, it is called uplink. So, receive part of the antenna will be seeing the noise, the transmit part of the antenna also will see the noise, but it is transmitting. So, it is not going to the receiver. So, the receiver noise is not getting affected by the transmit antenna, it is the receive antenna. So, the uplink antenna will see all these type of noise, and for the satellite generally on the average it is taken as 290 degree K. If it is looking to the other star or other purpose, then the communication for that communication noise has to be differently estimated. Let us go to that other part of the link, which is the earth station antenna. On the earth we have earth station, which now is at the downlink. Say we have a station and it has a radiation pattern and it is now receiving. So, it is on the downlink. So, we will see it is as a station antenna downlink will see the noise. Now, this radiation pattern, there may be side lobes and main lobes, there may be smaller lobes towards the ground also. So, therefore, it will see the noise coming out from the sky, also noise, this is the ground, noise coming from the ground. From the sky there may be clouds, there may not be clouds. So, let us see the first condition, which is during a clear day. During a clear day, the received noise at the antenna will see towards the sky mostly, which will see the galactic noise, which is all over the sky. You know, enormous number of stars are there. Some of them are visible in clear eye, are not visible in the eye depending on the other light, but the noise is coming. All around stars are there. So, there is a basic galactic noise which is there. In addition, there are noise sources, radio sources and radio noise sources. Major of them nearby is sun, then there is moon. There could be other radio sources which are generating noise, which will be coming. Now, if it falls in the main beam or some part of the beam of the receive antenna, that receive noise will be appearing to the antenna. Also, there is some noise which is coming from the ground depending on our elevation angle of the antenna, or it is either the main lobe or the side lobe. There may be some hills here that may give some noise to the main lobe, very small portion of the main lobe at low gain of the main lobe, or it may give it the side lobe, or from the ground itself the back lobe also will give. So, there is a ground noise. Also, other than the galactic noise and the planetary or other solar noises, there is atmospheric gas present in the atmosphere, which this beam is seeing. So, gas also will generate certain noise, gas noise, oxygen, nitrogen and other hydrometeors, rain, they also generate noise, which is not a clear day, of course. So, all these noises are picked up, and that will be appearing as a noise at the receiver station at the downlink. Right. Now, the sky noise was experimented, and it varies on elevation angle and the frequency in gigahertz, let us say, and let us say this is called the background noise, and let us say 300° K is here. This is 20 gigahertz. Let us say this is, let us say 60 gigahertz. This is, let us say 90 gigahertz. So, generally I will try to give a thematic plot at very low elevation angle. Low elevation angle, let us say theta is equal to 0°, just on the horizon. The noise is like this, sky noise, and at a little higher theta, it is like this. Let us say theta is equal to 10°. At much higher theta, which is, let us say, vertically above, it is like this, theta is equal to 90°. Now, there are a couple of things that we observe, that as I increase the theta from 0° to 90°, that is from horizon to the overhead, that is theta is equal to 0 is horizon and theta is equal to 90° is overhead. This sky noise is almost 290°, 300° K is here, almost 290°, most of the part of the microwave frequencies. And at low elevation angle, it reaches to very high, that is 290° or so. Now, there are also other things, like we are seeing two peaks here. One peak as at peaks, that is the noise peaks at around 20 gigahertz, there is a peak. This is due to the H2O molecules, that is water vapor, that generates some type of noise. And also we see other peak at 60 gigahertz, at around 60 gigahertz we get another peak, which is due to oxygen molecules. Now, they can be utilized for various purposes, but these are certain observations, these are measured values plotted. You can see these graphs in textbook, many of the textbook. So, that means it is varying on elevation angle, also it depends on the frequency. These are the two observations from the sky noise. Now, we can call this background noise as effective brightness temperature. It is bright, so called brightness temperature from sky. This effective, when I say, that means it varies with theta, phi, etc. We have seen at theta it varies at different elevation angle. At different angle, sun, moon may come, some galactic stars may come at different times. So, it varies with theta and phi. So, we got effective brightness temperature, which depends on one is spatial distribution, of background temperature, a curve we have seen, which you can term is as T background, which varies on theta and phi, and another distribution which is the antenna pattern. That is the radiation pattern, we can say, which we know directive gain d depends on theta and phi, which direction it is. So, in short, the earth station antenna temperature depends on couple of parameters. One is frequency. We have seen the curve, it varies with frequency. The background temperature varies with frequency as we change. There are certain peaks, some small lower temperatures also there, some places. Then it depends on elevation, azimuth, etc., and also it depends on atmosphere. That is, if there is a gas, rain, squalls, etc., it will have a different temperature. We will discuss that one in much more detail during our discussion on propagation. So, mainly it depends on the pattern and the background temperature distribution of that. Instead of going into the details of the theoretical or analytical way, we can straightway say system noise temperature of a receive system depends on receive antenna and receiver noise temperature. We have learned this one earlier periods, that receiver effective noise temperature. In short, I can say T system is T A, that is T antenna, and T receiver, which is nothing but T effective, the cascaded value of the receive subsystems. So, that is about the received noise temperature, and from the, as we see on the antenna side and from the receiver side put together, we have seen that how the system noise temperature that appears. So, we have discussed till now the power, signal power, and the noise power. Now, let us see that quality of service, what we are looking for, that depends on what we know: signal power and the ratio of signal power and noise power. And the receiver signal power, receive power, we have calculated, which is signal power, PR. Let us term it, it is a carrier carries the signal. So, let us call it C, and that we have seen, it is the transmit power multiplied by transmit antenna gain multiplied by the receive antenna gain multiplied by a term which we called path loss, because it depends on the distance from the transmitter and receiver and depends on the frequency of operation, that is lambda. So, this is what we have derived earlier, and also we now know that noise power is K T system noise of the receiver and the bandwidth on which it is operating. This is the system noise, which includes the antenna noise as well as the receiver noise. So, signal to noise ratio or carrier to noise ratio, here we commonly use carrier to noise ratio, is PT into GT into GR into 1 by 4 pi R by lambda whole square, and N is 1 by K T. In this case, instead of T S I am writing T and B. This T stands for system, receiver system noise. Remember, this GR is the receive antenna gain, not the receiver gain. GT is the transmit antenna gain, not the transmitter gain. Okay. So, this term, let us readjust this thing and let us see how the signal to noise ratio, or in this case always we refer to carrier to noise ratio, stands. So, carrier to noise ratio is PT GT, then I rearrange, I call it GR by T, and then I call it 1 by 4 pi R by lambda whole square, 1 by K and 1 by B. That K T B is there, and rest of things are transmit power. I have simply rearranged. There is a reason for rearranging. This one is our transmitter characteristics, and this one will see that is the receiver characteristics. This one is the distance, that is the path free space characteristics, and there is a bandwidth coming. Now, this bandwidth can be adjusted in a different way. Let's call there is a noise. Okay, first let us take the bandwidth this side. So, let us call it C into B by N is equal to PT GT GR by T 1 by 4 pi R by lambda square into 1 by k. This C into B by N, I can rewrite this one in a term I call a noise power density. In hertz, this I call it N0 as N by B, noise power by the total bandwidth. Okay, so it is watt per hertz. This is actually watt per hertz. Then let us rewrite and let us see how does it look like. So it will look like C by N0, that is equal to EIRP multiplied by G by T multiplied by 1 by 4 pi R by lambda whole square, which is the loss, multiplied by 1 by k. I can put it into d. The whole thing is coming out in hertz. In dB, if I write, then it will be in dB terms. It is C by N naught. It is in dB hertz. EIRP. It is in dBW plus G by T. It is dB per k, and then into 1 by 4 pi R by lambda whole square. It is a path loss which is actually in dB, and 1 by k, which is dB per k per hertz, right. So, since the time is up for this period, we will continue our discussion in the next period. Thank you.